Hello guys, I'm audible. Okay, so hello guys. So in this session, we are going to start ISRO previous year questions, and today we will be starting from 2015 paper. Means we will start from 2015 onwards. In this session, we are taking ISRO 2015 paper of strength of material and machine design. Right. So we will start with our strength of material. Here, when you look at the first question, so all of you can see my screen. Uh, okay. So now when you read the first question, this question is basically belonging to CFOs and bending moment chapter. They are asking the point of contraflexure is a point where what? So if you know, if you can answer, then please answer in the chat sections. I will explain. Yes. So yeah. So whatever the answer I'm getting, that is correct answer. The point of contraflexure is a point where the bending moment changes its sign, right? Or we can say the point where the bending moment just becomes zeros. So to explain this one, let me take one example. Here, if I take, yeah, correct. Option B is correct. Now to explain this further, let me explain with the example. So let me take example of cantilever beam. This cantilever beam is subjected to, let's say, W load, which are acting exactly at a distance L, and we have once again W at the free end also. We have one more moment also is there, W12. So when I, yeah, so when you look at this particular question, okay, so let me apply here the moment. Let me just reverse the moment. Here, if I take WL that is acting in this directions, that is the moment which I have applied. So here I'm taking point A, point B, point C. So now when you draw the bending moment diagram, so what you will be getting, first thing we have to calculate, that is nothing but the reaction force. What is the reaction force here? RA. Anyone can explain? Anyone can tell the answer for RA? RA will be summation of forces in the y direction to be 0, right? So here if I take RA minus W, that is equal to 0. So RA will be plus 2W. That 2W load is acting. What about the reaction moment? There will be certain reaction moment. Let me assume the direction like this. The reaction moment at A. So summation of moment about this A point to be 0. That is another static equilibrium conditions. So what we have here, let us assume the clockwise to be positive, anti-clockwise to be negative. So minus MRA, right, minus W into L plus W into L plus W into 2L. That is equal to 0. Let me take the moment WL by 2. So here also I'm taking WL by 2. Moment I have applied WL by 2. So what about the reaction moment? So 3WL minus WL by 2, 5WL by 2. So whatever the direction we have assumed, that direction is correct. Just check it out. Whatever the direction we have assumed at the support A, that is correct, right? Now let's start drawing with the bending moment. I'm starting with the free end, right? I'm starting with the free end. What is the sign convention? Very first of all, what is the sign convention for bending moment? Sign convention for bending moment. So here we have sagging bending moment and hogging bending moment. So here if I take any section in which the moment has been applied like this, then we call this moment to be positive bending moment. And whenever we have any section, if it is hogging bending moment, then we say this to be negative bending moment. The same concept we are going to follow for this case also. So bending moment at point C. So before calculating the bending moment at point C, you can see there is some external movement which are acting at point C, right? So if we take the right side of that beam, we are starting from the this side, right? We are starting our section from right to left. So when you just consider just to the right of C, there is a no part of the beam, right? So that is 0. But we are calculating once again bending moment at C. This we have calculated just to the right of C, just to the right of C point. What about the bending moment just to the left of C? Just to the left of C means not much away from the point C, just at the point C only. So we have what sagging bending moment of WL by 2. So plus WL by 2. Just check it out. Plus WL by 2. Then what is happening with the point B? What is happening with the point B? What about the bending moment at point B? Only one time calculation because there is a no external moment. When there is a no external moment, so only one time is sufficient enough to calculate the bending moment. So that is nothing but plus WL by 2. Because of this external moment, it is creating sagging bending moment, right? It is making the moment to be what? Sagging bending moment. But what about W? This W into L will create hogging bending moment, and according to our sign convention, that is nothing but negative. So when you just write, it will be coming it as minus WL by 2. So from C to B, what is happening? At point C, there is a positive bending moment, but suddenly point B, there is a negative bending moment, right? So something has happened in between that, right? So definitely point of contraflexure will be there at exactly between the point B and C, right? So let me, what about the bending moment just to the right of A? Just to the right of A means here. So here we have plus WL by 2, we have, sorry, we have plus WL by 2 minus W into 2L. minus W into L. So how much you will be getting? WL by 2 minus 3WL, that is nothing but minus 5WL by 2. That is a bending moment just to the right of A, but we have to calculate two times. Why we have to calculate two times at a particular point? Whenever bending moment is acting two times, whenever the bending moment is acting two times, remember we have to calculate bending moment at that point two times. So here, just to the left of A, just to the left of A means here. Here, what is there? Here we have this particular moment also will be acting, and that is nothing but acting like a what? Sagging bending moment of 5WL by 2. So here we can write minus 5WL by 2 already, which was acting, plus 5WL by 2. So finally answers would be 0. So that diagram will be closed. You can cross check it whether you are going in the right direction or not. Then you have to check whether at the end of the calculation of bending moment whether you are getting 0 or not. So here when you draw the bending moment diagram, you will be getting this. So here we have point A, point B, point C. Point C, how many values are there? 0 is there, plus WL by 2. Plus WL by 2. Then at point B we have negative, this particular value. Then further we have at point A 5WL by 2. We have further 5WL by 2. See, here at point A we have further 5WL by 2. But we have to draw with some different slope. This particular value. This is nothing but 5WL by 2. Right. So that's how you will be getting the basically what? Bending moment diagram. So why I have drawn the bending moment diagram? Because at particular point D you have bending moment. At point D just becomes 0. And this point is nothing but point D is called as point of contraflexure. Why we are calling point of contraflexure? See, because just to the right of D we have positive bending moment, just to the left of D we have negative bending moment, right? So here bending moment is changing sign. That means whatever the elastic curvature is there, that is being changing, from concave up to concave down, right? So or we can say concave down to concave up, or whatever the vice versa is there. That depends on the bending moment directions. If it is sagging, then we have what? Concave up. Whenever we have hogging bending moment, we have concave down. So that is the elastic curvature point of the things. But here, what I'm telling, whenever the bending moment is changing sign at a particular point, see here, point D just to the right of D, we have positive bending moment. Just to the left of D, we have negative bending moment. So that's how at point D it is being changing from positive bending moment to negative bending moment. That's why we are calling this to be point of contraflexure. Is that clear, all of you? Again, some of you might have confused here why I have drawn different slopes. See, whatever the slope here we have, this line slope theta 1, this line slope theta 2, both will be unequal. Why? Because this particular relationship, slope of the bending moment diagram will give me shear force. So whatever the shear force is there between A and B, that is not same as shear force between B and D. See here, let's say D point is here. So whatever the shear force here we have calculated, shear force here we have different values. That is very much clear, because whenever you calculate shear force in between A and B, you have W will also be added along with this particular W. You have two W, but between B and D you have only one W. So definitely slope is more for in between A and B as compared to B and D sections. Is that clear, all of you? Tell me this. Shall we move to the next question? Yes. Hello, hello. Tulsi, is that clear? Yes. Okay. So let's move on to the next question. So this particular question we got the answer as okay, B. Now here, when you move on to the next question, again, whenever you are preparing for ICRB exam, ISRO exam, definitely you should focus your attention on SOM plus fluid mechanics, fluid machinery, and then you have to be thorough with the topic called industrial engineering. So you should have focus on this particular subject, and you should also focus on industrial engineering. I will tell you the reason why the questions will be higher on this particular year, why the questions will be higher on this side. They will be inclined towards industrial engineering, right? I'll be telling you the reasons. But before that, we will solve some of the problem. A circular shaft of length L, it is being twisted basically by the amount 1 degree. That means angle of twist they have given was 1 degree. We can also write 1 into what? Pi by 180. That will be in radian. This particular shaft is having a length of 120 centimeter. We can also convert in mm. So here, I think no need to convert in mm, because let's keep everything in centimeter square, so that, or centimeter, so that we can get final answer in the radius of the shaft. Should be, we will calculate in centimeter, right? Let's see. So here we have a relationship T by J, tau by R, G theta by L. What is this equation we call? Torsion equation, right? This thing we call it as what? Torsional equation. Now here in this one, we will use this particular things. We will equate these two things. So what we can get? We can get R is equal to tau into L divided by G theta. R, if you want to calculate R in centimeter, what should be the tau value? Tau value, you can keep it in 1000 gram per centimeter square into length 120 centimeter. G value is what? 0. 0.8 into 10 power 6. Once again, kilogram per centimeter square. So again, that will be cancelled out by this particular unit, and theta will be pi by 180. So here, when you calculate, what is the value you are getting? 1000 into 120 into 180 divided by zero point 0.8 divided by 10 to power 6. So we are getting what? 27 divided by pi. We are getting the answer as 27 divided by pi. That should be in centimeter. Of course, in examination, uh, the exact question I don't know, but whatever the scenario is looking right now, based on that, it is not very much clear in which unit they are asking this particular value. So I'm assuming that they are asking in centimeter. So this D should be correct. If this would have been in mm, then 270 by pi. But 270 by pi, there is no option. So that should be in centimeter. Modulus of rigidity is nothing but one of the elastic property, right? Modulus of rigidity. One of the elastic properties of a material. Can I move to the next question? Is it done for all? Okay, let's move on to the next question. Here again, they are asking the question from strength of material. So here they have given one frame. The frame consists of two arms of equal length L and L, which is shown in the figure. The flexural rigidity of each arm is EI, right? What is the meaning of this? EI. The flexural rigidity of each arm is same. That means you can say cross-sectional area and material is both, for both the parts. You can consider part A, B, C. So for A, B, and B, C, material is also same, and we have what we call cross-sectional areas. That means whatever the dimension is there, that is also same, right? Even if it is different, but the EI product, right? The EI product is same for both AB and BC. For AB and BC, it is same, right? That is they have given as EI, right? Now, once again, the vertical deflection at the point of application of load. That means they are asking vertical deflection here at point C. So, whenever any frame question is given to you, any frame or any structural component, right? And whenever they are asking vertical deflections, always use strain energy method. And I will tell you shortcut to do it in a very quick amount of time, so that even though method is lengthy, but you can solve it in examinations. Here you have to assume that whatever the BC is there and AB is there. I'm drawing once again this particular diagram to be here. So here we have AB and C. Here we have load P. Here we have this one. Here we have length L. So for basically, what is the strain energy method? The strain energy method is nothing but it will tell you, first of all you calculate total strain energy. First of all you calculate total strain energy. Here it will be BC plus AB, right? Whatever the total strain energy will be there, that is there because of what? Both the member AB and BC, right? After that, what you do, if you want to find the deflection at point C, you try to partial differentiate this total strain energy with respect to load P, and that will give you vertical deflections, right? And what is the strain energy formula when the beam is subjected to bending? We know that m square dx divided by 2ei, from 0 to whatever the length is. So directly, if I just differentiate here, dou u by dou m, right? So here what I will be getting, 2mx dou m by dou p into dx divided by 2el, 0 to l. So finally, what I will be getting here, you just calculate mxx, differentiate with respect to p, multiply dx divided by ei. That's it. Now, as compared to calculation of this particular step is very easy. I will tell you why. So first of all, calculate the bending moment in BC member. In BC member, take any section at a distance x. So what you can calculate, minus p into x. Why minus? Because according to our sign convention, that is coming it as negative. That is a hogging bending moment, right? You differentiate also with respect to which load? P load, right? So you will be getting what? Minus x. That is done. What about AB member? AB member, when you look at very clearly, AB member, you have my different, when you transfer the load P to joint P, whenever you want to transfer the load, whenever the two members are connected and you want to transfer the load at point B, you simply apply two loads, equal and opposite directions. Here, you just apply P and P. This P will cause the downward load P, but what about this P and this P will create the bending moment. In which direction? In these directions. Like this, P into L. Now this particular beam will be simply supported beam subjected to end moments. One end moment, there is a moment is acting, but it is acting like a simply supported beam, right? So what we can have here, we have to calculate the reaction forces. Let's say here RB, here we have RA, right? So definitely when you try to see, I'm just converting into equivalent diagram. Here there is a P, there is a moment PL. So I have simply rotated diagram by 90 degree. Actual diagram is vertical, right? Do not confuse. Here A, B. Now you try to calculate reaction RA and the reaction RB. So that's a very simple. You take summation of moment about A point to be 0. Then you can calculate what? P into L, that is equal to RB into L. So RB will be what? P. This RB will be equal to P. This RA will be what? In the downward directions. That is also equal to P. Now take any section and calculate the bending moment in this AB member. So I'm taking the section here to here like this. So what about this bending moment in this particular AB member? First of all, hogging bending moment PL is acting plus P into X, plus P into X will be acting, right? Plus P into X, because that is acting like a sagging bending moment. Now do not consider axial strain energy. I'm not considering any axial strain energy because that is very very small as compared to bending strain energy, right? So here once again you try to you can write P into X minus L. That is the bending moment which are acting in AB member. Now you differentiate with respect to load, you will be getting X minus L. You will be getting what? X minus L. Now my dear friend, what you can write further? What you can write further? Here, total strain energy you have differentiated with respect to load P, that you can write it as dou U by dou P. Sorry, here you have to differentiate with respect to P. You have to differentiate with respect to P load, right? So dou U by dou P of which member? BC member, plus dou U by dou P of which particular member? AB member. That will be the total differentiation of strain energy with respect to load P. Dou U by dou P of BC member is what? BC member is what? Here we have load that we already written the formula. What is 0 to L? In BC member, if you use this particular formula, here. MXX in BC member minus P into X. And what is our dou M by dou P? Minus into X into dx divided by what? EI plus 0 to L. In AB member, what is the load which are acting? What is the moment? P into X minus L. What about the C? MXX we have written dou M by dou P. Once again for AB member is what? X minus L into dx divided by EI. Now only we have to do what? We have to integrate, right? So further we can write 0 to L, deflection at point C will be minus P into X dx divided by EI. This is nothing but for BC member. This I am writing for AB member, right? 0 to L, P into X minus L whole square dx divided by EI. So what we can write further? P into XQ divided by 3EI 0 to L plus P divided by EI. Now when you just open this one, what you can write? X minus L whole square will be what? X square plus L square minus 2XL, right? So further what you can write here? X square plus L square minus 2XL dx 0 to L. PLQ divided by 3EI LQ divided by 3 plus L square into L minus 2 into L X square divided by 2 0 to L. So PLQ divided by 3EI plus PLQ divided by 3EI plus PLQ divided by EI minus PLQ divided by EI, right? So this will cancel out. You will be getting what? 2 PLQ divided by 3EI. So this will be the answer for deflection at point C. This is not a very lengthy method. Again, do not think that it is a very, very lengthy method. Again, I told you, when you try to write total strain energy and when you write mx square dx divided by 2ei, when you do by this method, it is very lengthy. But when you try to simplify and when you write dou u by dou p format, it is a very, very easy task. Again, when you think that, sir, I'm not able to solve this question within fraction of second, then that is not a very good way of thinking. If it is a good level question, then you cannot expect to solve this question within 1 minute, right? You need to have enough practice of each and every method before exam, right? So that you can solve very quickly. Your calculations should be very, very fast. Now, again, there is one more method called superposition method. But if I tell you that method, many of the candidates, they will not be able to understand, right? So simply leave that, keep it very simple and try to solve by this particular method only. That is a strain energy method. Is that clear? In many places, the answer is given, might be given answer as C, but that is wrong. Because this question is belonging to what? Basically, they have taken from mechanical 2009 question. Gate mechanical 2009, right? So sometime ISRO basically took the question from the gate examination also previously. But that will repeat or not, nobody can predict. But at least you try to solve wherever you finish any subject. Let's say strength of material we are revising, so you try to finish gate previous year question also along with if you are doing any other sources. Let's move on to the next question. A thin basically cylindrical cell of diameter d and the length L and thickness T is subjected to internal pressure P. The ratio of the longitudinal strain to hoop strain. The ratio of the longitudinal strain to hoop strain they are asking. All of you can see my slides. So a thin is basically cylindrical cell. There will be two types of stress that will be developed. Whenever you consider, let's say, if I draw the diagram, so there will be certain call internal pressure here also it will be acting. Internal pressure at the ends plate it will be acting, right? So because of this there will be certain called hoop stress. Because of this there will be something called longitudinal stress will be acting. Because of these two, there will be strain also, right? There will be strain also that will be developed. First, we will call this to be hoop strain. That is nothing but sigma h upon E minus mu sigma L upon E minus mu sigma R upon E. But generally, in case of thin cylindrical pressure vessel, we neglect radial stress. We neglect whatever the radial stress value. That radial stress is nothing but what? Minus of pressure value, right? So, but this pressure value is P is very, very less as compared to what? Sigma H and sigma L. That's why in comparison of that, we neglect this radial stress. But in ISRO examinations, let's say for 2023, they will be asking you what is the formula for hoop strain, and they might be giving you four options. Like let's say they have given the option sigma H upon E minus mu sigma L upon E. B option they will give sigma H upon E minus mu sigma L upon E minus mu sigma R upon E. So do not click the option A. That is wrong. Option B is correct. Even for a thin cylindrical pressure vessel, if they will be asking you, exact formula for hoop strain, do not tick option A. Even after challenging also, they will not accept. Right? So please try to tick the option B. After that, we have assumption that radial stress, that is nothing but minus of P value. That is a secondary thing, right? Because of thin value, because of thin thickness is very, very small as compared to internal diameter. In such a scenario, we neglect the radial stress. But in reality, whatever the formula is there for designing, we take option as B. Now, coming back to this formula for hoop strain, what we can write? Hoop stress, we know that PD divided by 2T. where d is nothing but internal diameter, and whatever the t is there, that is nothing but thickness. Longitudinal stress will be PD divided by 40. So here when you write here PD divided by 2T minus mu PD divided by 40E. So what is the hoop strain? You can write further. Here they have taken whatever the value of C here. Uh, Here I think M they have given, in this question M they have given as 1 upon mu, right? M is given as 1 upon mu in this particular formula. Whatever the option they have framed, they have taken M as equal to what? 1 upon mu. So further, if you want to write, so what you can write here, PD divided by 4TE, we can write 2 minus mu. What about the longitudinal strain? That is nothing but sigma L upon E minus mu times of sigma H upon E. PD divided by 40E, PD divided by 2TE. So here we can write PD divided by 40E, something like this. So this thing we got it from here. Further, they are asking what is the longitudinal strain to hoop strain. So what they are asking, hoop strain to longitudinal, sorry, longitudinal to hoop strain they are asking. So PD divided by 40E, 1 minus 2 mu, PD divided by 40E, 2 minus mu. So this will cancel out. So what you will be getting, 1 minus 2, 1 upon m, 2 minus 1 upon m minus 2, 2m minus 1. So when you just look at the longitudinal strain to hoop strain, you will be getting as B. No, here we have m minus 2 divided by 2m minus 1. So A will be correct. Take it out. Are you getting A? Tell me guys, is that clear? Shall we move to the next question? Okay. So one more thing I'm giving you as a note point. Yes, A is correct. One more thing you just note down as a note. See, hoop strain will give you change in diameter by original diameter. Longitudinal strain will give you change in length by original length. But if you want to calculate change in thickness by original thickness, that you cannot do by school mathematics, like volume is something like a pi dt, or maybe whatever the we have formula for calculating the change in volume by original volume, and by that first you calculate a change in length by original length, change in diameter by original diameter. And if you're thinking that I can do by using that school mathematics change in thickness by original thickness, then you are wrong. You have to calculate the radial strain. Once again, the formula will be sigma r upon E minus mu sigma h upon E. Please note down, because ISRO is not like they will repeat previous year questions. So definitely they will be adding some new things either from the gate or from the book. Radial stress we take it as 0. So whatever the change in thickness by original thickness will be there, that is calculated by using these particular formulas. So minus mu by E, PD divided by 2T plus PD divided by 4T. So you can note down minus 1 upon m into E. You can write it as 3 PD divided by 4T. This will be the formula, where M is nothing but 1 upon mu. Or you can write mu is equal what? 1 upon M. Note down. Again, this particular discussion is valid whenever we have horizontal cylinder. When this horizontal cylinder is being what? Basically closed by the plate, end plates, right? But suppose there is an open cylinder. If there is an open cylinder like this, whenever we have open cylinder, at the end we don't have any plates, right? So here the pressure might be acting. So whenever the pressure is exerting, so pressure, whatever the material is there, that material will be pressurized, right? And because of that, there will be hoop stress will be generated, but longitudinal stress will be zero, because there is a nothing called plate where the pressure can be exerted. So for the open cylinder, longitudinal stress will be zero. So put a note point and note down. Even in this scenario, or whenever you have a vertical cylinder, it is just placed like this. You have the liquid of certain height h. So in this case also, at any point whenever you want to calculate, here whatever the pressure is there, that is being fully resisted by reaction force R by the ground. So there is a no force that will cause that, there is a no net force which will cause this plate to be resist in the longitudinal direction. So there is a no resistance required in the longitudinal direction. So again it is zero, but hoop stress will not be zero. So note number 1 and note number 2. Now can I move to the next segment? Next question. So here when you look at a simply supported beam carries a load P through a bracket. Here we have some bracket. Here let's say A, B, C. So whatever the BDE is there, BDE, that is acting like a one bracket, right? And in that bracket, one load is applied at the ends, P. Now they are asking what is the maximum bending moment which is being acting, right? What is the maximum bending moment they are asking in the beam? So for that, let me take separately here A, B. Here we have B. Here we have C, BDE. So now when we take the dimensions, there is a dimension of A. Here we have L, L by 2, L by 2. And of course, we do have the reaction force, RA and RC. So very first of all, we have to transfer the load. Whenever this type of question is coming, right, whatever the joint is there, just look at the joint which is being connecting this bracket to what we call this bracket to the beam. At that particular joint, you introduce two load, P and P. No harm is there when we introduce two equal and opposite load, right? So now when you convert into equivalent diagram, what we can get here, there will be Ra and there will be Rc. So because of P, the P is acting already in the downward directions, this P, but this P and this P will create some movement. In which directions? In these directions, P into A. And that's how we transfer the load A, B and C. Now the bracket you can remove, because we want to calculate the bending moment in the beam, right? So we have to see the effect of all the moments, all the loads acting on the beam, not on the bracket. If they would have been asking the bending moment for the bracket, then we would have been done by using taking some section, but here they are not asking for the bracket, they are asking for the beam ABC. So that's how we have transferred the load from bracket to the beam. So here when you calculate the reaction force very quickly, what you can do, you can do summation of moment about A point to be 0. So P into A plus P into L by 2, that is equal to RC into L. So what is the RC value? RC value you can calculate P by 2, P by 2 plus PA by 2, right? And what about RA? Because you know that summation of forces in the y direction to be 0. So RA plus RC, that is equal to P. So RA will be what? P minus P by 2 minus PA by 2. So you can calculate P by 2 minus PA by 2. That is the reaction force that is acting at A. Simply, I told you the rule how to draw the bending moment diagram, right? I told you, right? So either you can start from the right to left or left to right. So we are habituated, let's say, from right to left. I'm following this one. So what you can do, you can follow here. Now bending moment at point C. Only one time calculation because there is no external moment. So at point C, we are calculating the load into distance, but there is no distance. So again, that is 0. Force is there, but there is no distance. What about the bending moment at point B? But for the point B, you see there is external movement. So we have to calculate two times. One onto the right of that, one to the left of B. First, I'm calculating moving from right to left. I'm just calculating right of the point B. This is the left one. At the right of C, when I am moving like this, I cannot see this movement which are acting, right? I can only see that the reaction force RC is there and which has certain value, and that is creating sagging bending moment, that is RC into L by 2. But what is the RC value? P by 2 plus PA by 2 into L by 2. That is the bending moment which are acting at point B. What about the bending moment? But this is the bending moment which are acting at point B, just to the right of B. What about the bending moment just to the left of B? Just to the left of B, same values there, but there is a certain call moment which will be added here. See, when you just see here, you can see very clearly this movement, and that is creating like a sagging bending, a hogging bending moment. See that? Hogging bending moment. So what we can write minus P into A. So here when you write PL by 4 here. Here you can write PL by 4 plus PAL divided by 4. Here you can write PA by 4 minus PA, something this particular value. So what you're understanding? Out of this value is what? Little bit smaller one. So when you draw the bending moment diagram, you can draw here. This is the A point, B point, C point. At point A, we have bending moment 0. At point C, bending moment 0, right? At point B, we have two values. One is just to the right of A. When I move from here to here, we have certain values, and that is a big value. What is this value? This value is nothing but this one. But suddenly, at the same point, we know that it is being reduced by the amount what PA, because there is a moment that is acting like a what hogging bending moment. So because of that, that is being getting reduced, right? So once again, we have joining from here to here like this. So this is your bending moment diagram. Positive. So here when you calculate the value of the bending moment, that is the maximum, right? So at the point B, you are getting two values. One is this value, other is this value. They are asking maximum. So whenever at any point two bending moments are acting, always take maximum value of that, because for that only you have to design the beam, right? So here the what is the maximum value? Maximum value will be this one. So in which option it is there? PL by 2 plus AP by 2. Here when you see the option, I think there is a mismatch in the option. So here there has to be some half. Note down. C will be correct. Here, sorry, here it should be PA by L, right? This should be PA by L. That should be PA by L. Then it should be again PA by L, right? That should be PA by L. So here we have PA by L. So we can just do correction here. Now, here also we have PA by L. So here we can just calculate. You will be getting answer it as what? PL by 4 plus PA by 2 minus PA. So PL by 4 minus PA by 2. So out of these two, this is the maximum value. Is that clear, all of you? Is that clear, all of you? Can I move to the next question? Okay. So now when you just look at the question number 10, this is a simple question. What is the answer for this? A vertical column has two moment of inertia. Here we have, let's say, support where it is subjected to some axial compressive load. Because of that, there will be certain called buckling will happen. Right. Now this buckling will happen if I just consider the cross-sectional area of that B of this particular beam, whatever the column is there. Let's say the cross-sectional area is a rectangular one, where IXX like this, IYY like this. So whenever the column will buckle, the column will always buckle in the direction of least moment of inertia. Why it will buckle only with respect to least moment of inertia? That is a very simple thing. Moment of inertia is nothing but one of the geometrical properties of the any material, any cross-sectional, any particular material you take. That is one of the geometrical properties, right? We also call this to be second moment of area. So basically, it is saying that physical significance is that it is resistance of any movement which are acting on a particular material, right? The more and more amount of moment of inertia, that more and more stability of particular material, right? So that's why whenever you see flexural rigidity, right? Whenever we say flexural rigidity, EI value will be higher and higher, more will be the bending strength. More and more will be the bending strength. That means very difficult to buckle, very difficult to apply the, very difficult to deflect by the bending moment. And whatever the column is there, that is also, you can see lateral deflection is there, right? And that is also being same. Whenever you try to derive the critical load formula, you will see there is a bending which are also happening, right, in the same of what we have seen in the beam, right? So there is a very slight difference between beam and column. In the beam, we subject the beam to transverse load, right? Whatever the transverse load which are acting. But in column, we subject that column to be axial compressive load. right? Now here, so that is the one thing. But physical significance of moment of inertia is that they resist whatever the moment is there, right? We cannot more and more moment of inertia. Very difficult to bend that material by applying the bending moment, right? So very difficult to buckle it in case of column if it is having more moment of inertia, right? So here, if I take one example of B and depth is D, so when you calculate Ixx, here you will be having D BQ by 12. When you calculate Iyy, you will have BDQ by 12. So what you are understanding from here that D is much more than B. So definitely Ixx will be lesser than Iyy. Right. So definitely whatever the column is there, that column will buckle about least moment of inertia, that is Ixx. Not a very difficult task to buckle when it has certain moment of inertia which is lesser in certain directions as compared to other directions. That means if you draw the cross sections, it may like this. That means whatever the buckling will happen, that will happen in the plane of a laptop screen, whatever you are observing. Not buckling will not happen out of the plane. In a plane section, out of the coming perpendicular to the laptop screen, right? Within the plane, it will happen. So definitely, you can see here, Ixx should be whatever the buckling is there. That is buckle should happen about Ixx, right? In the plane of cross sections, in the plane of whatever the diagram we have drawn. Now, no, in square sections, whatever the it will buckle about both the axis, x and y, as it has same thing is there. So in that scenario, whenever we have a square cross section, so we have to see uh, depends on the application. Depending on the application of the column, we will try to see exactly where we want to restrict the deflection. Whether we have to restrict the deflections in the plane of laptop screen, or I want to restrict the buckling in the perpendicular plane, in a perpendicular plane of what we call laptop screen, right? Depending on that, we subject whenever we have more and more amount of buckling in any column, we try to restrict the buckling by adding some additional support like this, in the form of like this, maybe in between of that, so that whatever the deflection is there, at least that can be reduced. But that is a different case I am talking about now. Here, note down the next questions. Which of the following theories of failure is applied to brittle material? Now, very first of all, we have different types of theories of failure, right? The big question mark: why we have different theories of failure for a material? Why not only one theories of failure is there, right? Let's say we have only Newton's law, so only one law is there, right? Let's say we have, of course, we have three law, but only one name is there, Newton. But here, when you observe, Rankine is there, we have von Mises is there, whenever we have Trescas also. So different scientist names are associated with different theories of failure. But the question is why different theories of failures has been proposed. So it is like an opinion given by different person, right? For suggesting the failure of a material. Some materials are very strong in tension. Some materials are very weak in tension. Some materials are very strong in shear, but some materials are very weak in shear. Again, some materials are very strong in compressive load, but some are very weak in compressive load. So they have given different opinions, like we tend to give opinion whenever a person fails. Then in a society, so many members are there, right? So they will be start telling you the different reason for a failure of candidates. Some will say because of lack of practice, some will say lack of concentrations, Some will say he or she might be distracted. So likewise here also for material, some scientists they said that materials are failing because of the maximum principal stress. Some said that no, material might be failing because of the maximum strain energy exceeding the strain energy that is being that is the capacity of a material to store, right? If it is exceeding beyond that, then the material gonna fail. Some said that no, material having certain capacity, certain yield shear stress. If it is exceeding the maximum shear stress, if it is exceeding the yield shear stress, then we say the material is being failed. So it depends on the different I know uh, basically what we are considering for considering the failures of a material. So bitter materials are very weak in tension, no, very weak in tension. In contrast of brittle material, when you take ductile material, it's a very strong in tension, right? In metal forming we use ductile material, we don't use brittle material because we cannot make it form in any other shape. If you want to transform from one billet form to another, let's say from the raw material to some used product, then we cannot do for the brittle material, it will break. So if it is a very weak in tension, then we try to calculate what is the maximum value of that tension value, right? Whatever the maximum value of that tension, we try to calculate so that we can think of what should be the maximum tensile stress because of that it is failing, right? And out of all the theories of failure which they have mentioned in the option, only maximum principal stress theory, that is we also call Rankine's theory, they have considered maximum principal stress. And according to this, they have said that if sigma 1, if it is more than yield stress, then we say the material is failed. If it is less than yield stress, then we say material is what? Safe, right? So this is the best theories for what we can say that can be applied to brittle materials. Because whatever the diameter that is being given by this theories of failure is exactly or almost equal to experimental values which we have done on brittle materials, right? So maximum says this theory, it is good for ductile material. For ductile material, if somebody will be asking you best theories of failure, so that is nothing but maximum distortion energy theory, that we also call von Mises theory. No doubt, very important. For a hydrostatic state of stress, the good theories of failure is nothing but maximum strain energy theory. We also call Higgs theory for hydrostatic state of stress. Whenever you keep any material to be in the water, right? In that case, because if you use maximum shear stress or any other theories, it will give you wrong prediction about the dimensions. Okay. Now try to see once again this question. So here, once again, they are asking for a component loaded with the force F, the axial stress at the corner point P. At the corner point P, they are asking what is the axial stress. Again, they are asking in AB member, right? Let's say ABC. They are asking in AB member, but the load is acting on a BC member. So we have to transfer the load from BC to AB member, right? So once again, here we have to transfer the load from AB member to BC member. How we can do? It's a very simple. I told you the trick of transferring the load. Whenever we want to transfer the load from any point to joint point, you introduce two equal and opposite load. And what will be the equivalent diagram? Equivalent diagram will be, sorry, if I want to draw the diagram only for AB member, then there will be tensile load and there is a moment. Moment nothing but P into L. But wait, here exactly we want to transfer exactly to the center of gravity of this beam. So here we want to transfer the load. So I need to introduce two load, right? So this P are exactly equal to what? F only. So let me write F into L minus B will create the bending moment, right here. F into here. Sorry, the load is what? F. So everything will be what? F. So this is the moment which we have transferred, and we have transferred the load, and because of transferring the load, moment is coming here. AB. Now it's a very simple task to calculate what we call axial stress. Axial stress at a particular point P on the up. See here, when you look at this fiber AB will be subjected to um, hogging bending moment. Because of that, it will bend like this. It will bend like this. So upper fiber, whatever the upper fiber is there, that is being subjected to a tensile load, and bottom fiber will be subjected to what? Compressive load. Point P is there on the what? Top fiber. Point P is there what? On the top fiber here. Here somewhere here we have the point P. Let's say here we have the point P. And the point P is subjected to what? The point P is subjected to tensile bending stress, axial bending stress, right? So here we can write net axial stress will be, because of this F, there will be what? Central axial stress will be developed, F divided by area plus M into Y divided by I, right? What is the F? What is the area which will be acting? 2B into 2B plus moment. What is the moment which are acting? F into L minus B. What is the distance? What is the distance of a particular point P with respect to this? Will be B. This will be the, let's say, the neutral axis. This will be the neutral axis, my dear friend. So this will be what? Y will be what? B only, right? Y will be what? B only. And what about this moment of inertia? Moment of inertia, we have to calculate about here. If we just take the moment of inertia, about which axis we have to calculate? Let's say this is the YY. Let's say this is XX. Fortunately, here either you calculate IXX or IYY, both are coming out to be same, right? So 2B into 2BQ divided by 12. So here we can write F divided by 4B square plus F into, here when you simplify, you will be getting F into L minus B. This B will cancel out. So here I'll be getting BQ 12 divided by 8 into 2. So I will be getting what? F divided by 4B square plus 3 by 4 F into L minus B. So if I multiply B here with the B here, so what I will be getting? F into B plus 3FL minus 3FB divided by 4BQ. So finally what we can get? See, because of this F force, there is a tensile load, tensile stress, and P point is subjected on is situated on top fiber. Top fiber is also subjected to what? Uh, Tensile bending stress. So both will be added together. So finally, 3FL minus 2FB divided by 4BQ. So final answer will be what? F 3L minus 2B divided by 4BQ. This will be the answer. Note down. Whenever remember, whenever the question is coming of transferring the load from any member to any other member, you try to see the connection point where they are connected. Here you introduce two equal and opposite load like this. This F will be coming downward, and this F will create the bending moment in these directions. Whenever you want to transfer from any load to any other load, whenever you have any load like this P, right, you want to transfer here at point B, see the joint and introduce two load like this. So one load will be coming downwards, other will create the bending moment like this. For any structure, remember, that is only the fundamental thing. Here they have given the diameter of shaft B is 2 times the diameter of shaft A. The ratio of the power which can be transmitted by the shaft A to the shaft B, same material means what? G of A will be same as G of B, that is equal to Z. So power is what? Power we know that 2 pi nt by 60, right? The speed at which both are rotating are assuming to be what? Same material. So power is what? Directly proportional to torque, right? So, and we also know that tau is what? 16T divided by pi dq. So T is what? Directly proportional to dq. So power will be what? Directly proportional to dq. So here we can write PA divided by PB, that is equal to what? TA divided by DB to the power cube. So here dA is what? 1 upon 2 times of cube. So 1 upon 8 times of this. B option is C option is correct. C option is correct. So whatever the shear stress which is being introduced, the shear stress I am assuming that it is also same for both the shaft A and B. Okay, that's a very simple one. The massless beam, that means weight of the beam is not considered, only the load effect, external load effect is being considered. The beam is of rectangular cross sections of width 30 mm, height to be 100 mm. Okay, so you have read the problem. See here, RARB, and there is a uniformly distributed load which are acting of 3000 Newton per meter. So do not think that you have to take this much of time. For explanation, I'm taking time, right? You have to be, you have to have enough practice so that you can solve all this thing, bending moment calculation and all very fast in examinations. You will not be having that much of time. Before that, you try to practice enough. So here RA and RB will be what? So directly you can calculate. I'm writing the value. RA value is what? 1500 Newton, and this RB value is coming it as 4500 Newton. Right. So what they are asking maximum bending stress. Maximum bending stress, we have to calculate maximum bending moment. And how to calculate the bending moment here? At point A, bending moment is 0. At point B, bending moment is what? Once again 0. Let's say at point C, what is the bending moment which are acting? At C, what is acting? Which I'm calculating from left to right. Left to right I'm moving. So RA is what? RA is 1500 into 2. That will give me 3000 Newton meter. That is a sagging bending moment. What about the bending moment at point B? Of course, that is 0 only. We have already calculated. But whether this 3000 Newton meter is maximum value or something else we will be getting, for that I need to check whether shear force is getting 0 or not somewhere. In this section, let's calculate whether shear force is getting 0 or not, right? So I'm just calculating shear force at that section XX by taking section X from the right support. RB is what? Minus 4500 plus 3000 into X. Whether it is getting 0 or not, yes. And I'm getting the value as 45 divided by 30. So at a distance 1.5 meter, I am getting shear force 0. And we also know that shear force is what? Dm by dx. The moment shear force is 0, the slope of the bending moment diagram will be maximum. The slope of the bending moment diagram will be what? Sorry, slope of the bending moment diagram will be 0. If shear force is getting 0, at that particular point, there is a high chance that bending moment will be what? Maximum, because dm by dx is 0. And from mathematics, whenever any y is there, which is a function of x, if you want to get maxima and minima, for that you have to do dy by dx equal to 0. Right? So exactly at 1.5 meter, I will be calculating the bending moment. Let's calculate. I am keeping the point E at a distance what? X is equal to 1.5 meter from the right support. From the right support. So what you can calculate? RB. RB is what? Minus 4500 Newton plus 3000 into 1.5. That is a load, right? That is a load, but 4500 into what? Again 1.5 into 1.5 divided by 2. So when you calculate how much of value you are going to get, 4500 into 1.5 minus 1500 into 1.5 into 1.5. So I'm getting what? 3375. 3375, that is minus. No, Newton meter. Minus 3375. Minus or plus? Fifteen hundred into 1.5 into 1.5 minus 4500 into 1.5. Just check it out. This 4500 should be positive. This should be negative because that is like a sagging bending moment and hogging bending moment, right? Uniformly distributed load will create hogging bending moment. This RB will create sagging bending moment like this. So this should be plus. So whenever you draw the bending moment diagram, you will be getting what? A straight line from A to C. Then you will be getting something like this. Here you have maximum value 3375, but here you have the value 3000. So maximum value is what? 3375. So for a maximum bending stress, maximum bending moment need to be considered. M into Y maximum by I. I about the neutral axis. So what is the maximum bending moment? 3375 into 1000. Y. Y is what? Y maximum is what? Y maximum will be here. That is 50 mm. This is the vertical bending case. So it will bend about this neutral axis. And moment of inertia will be what? 30 into 100 cube divided by 12. 30 into 100 cube divided by 12. So now when you calculate, you will be getting answer as 67.5 megapascal. 67.5 megapascal you will be getting answer. That is the maximum bending stress. Now we will try to calculate the we will try to calculate the next question. Here, PL cube divided by 3EI is the deflection under the load P of a cantilever beam. Cantilever beam subjected to end load A and B, right? So strain energy due to the bending they are asking. That is a very simple. At any section, when you want to transfer the load, at any section, if you want to calculate the bending moment, then what we write? Minus P into X. Strain energy they are asking. So strain energy because of bending, we know that mxx square dx divided by 2ei. So we can write P into X whole square dx divided by 2ei. So we can further write P square divided by 2ei x cube divided by 3 from 0 to L. The total length is what? L. P square L cube divided by 6ei. B is correct. You can also calculate, I told you, right? Delta is what? Dou u by dou p. So delta into dp will be what? Let's say du. So simply you do PL cube divided by 3EI into dp, that is equal to u. So u will be what? P square L cube divided by 2 into 3EI. Right? Like that also you can calculate and you will be getting same answer. Because P into dp integration will be what? P into dp integration will be P square divided by 2. That is a simple one. Here we will be starting the machine design. See why different. Static friction is low in what? In hydrostatic lubrication. Why? The very big question is why. Why static friction is very low in this particular hydrostatic bearings? See, in a bearing we have a lot of types of bearing, right? I will discuss in the next segment when we start 2016 paper of ISRO. In that, I will take a small session for types of bearing, right? Types of bearing. Here we have two types of mainly bearing. One is a sliding contact bearing, other is a rolling contact bearing. Right. One is a sliding contact bearing, other is a rolling contact bearings. Again, anti-friction bearing or rolling contact bearings, we have ball bearings and what we call roller bearings. In case of sliding contact bearings, based on the lubrication, we have zero lubrications, thin lubrication, and we have thick lubrications. Zero lubrications, in which we don't require any lubrication. See, what is the purpose of the bearings? Suppose there is a shaft which is being rotating. The purpose of bearing is to support the rotating member called shaft. That is the only purpose of bearing, but that is a very big purpose. Zero lubrication, we have a thin lubrication, thin film lubrications we call. Then we call thick film lubrication. Thick film lubrications. Note down. Thick film lubrications. In case of thick film lubrication, further we have two types. One is a hydrodynamic bearing, other is a hydrostatic bearings. One is a hydrodynamic bearing, other is hydrostatic bearings. Hydrostatic bearings, my dear friend, in case of hydrodynamic bearings, whatever the metal to metal contact, this metal to metal contact is avoided with the help of lubrication, but this can be avoided by the action called wedging action. This metal to metal contact is avoided by the lubrication in hydrostatic bearing by some pump. Continuously with the help of pump, we are supplying what? Lubrication in between shaft and bearings. Right? Hold on. So that is a you have to remember what we call starting friction. Starting friction is very low in case of hydrostatic lubrications. Hydrostatic lubrications. Okay. As I told you, I will discuss more in detail, right? So that you can understand why static friction is low in our next segment, in our next class. Note on the next thing. Which of the following is a trapezoidal thread we have? Acme. We have different types of thread. Note down. We have different types of threads. Here, when I take the example, note down. We have square thread like this. We have Acme thread. Note down. Because of form of the shape is trapezoidal, that's why we call this uh, thread to be trapezoidal threads. Acme thread. Note down all the important points. Whatever the included angle is there, right? Here included angle. This included angle is 29 degree. Other threads we have nothing but we call buttress thread. Here we have thread profile in the form of something like this. Sorry. But whatever the included angle here we have included angle, note down, it is a 45 degree. It is a 45 degree. Here this one is what? 29 degree, but here we have 45 degree. What is the square thread application used in screw jack? Among all, it is having highest efficiency for transferring the power. If they will be asking you which type of thread used in lead screw, the lead screw of a machine tool, what you will answer? Again, we will answer the answer called acme thread or trapezoidal thread, right? Application note down. The lead screw of lathe machine. These threads are used in power press machines. One more special thing, it can transfer the power only in one direction. But when you just compare buttress and acme thread, in acme thread we can transfer the power in both the directions, in either directions. So these are the application and few more points related to types of threads. Okay, here wrote down the second last problem. What is the tearing efficiency? First of all, we have to calculate tearing load. What is the tearing load formula? Whenever you have two plates that is being, let's say we are doing with the butt joint, we place it by bolt, right? So because of the placing the rivet into the plate, there might be certain call riveting hole will be there, but because of this riveting, these edges are getting cracked. When we apply tensile load, these edges are getting cracked, let's say diameter is d, the diameter of the rivet, not diameter of the rivet hole, I'm calling diameter of rivets. So here tearing load that can tear, you know will be pitch. From here to here, I'm calling this to be distance to be what? Pitch. This I'm calling this to be pitch. So P minus D of hole into what? Thickness into sigma T. That is the area. See, this is the thickness T, and if I apply tensile load, my dear friend, what is going to happen? What is going to happen? Definitely, it will tear off. And based on per pitch calculation, how much of rivets are there? Half and half. Half and half will become full half, full one, right? So this half and this half, if you just combine, it will be what? Complete one rivets. diameter of hole. That's why I'm writing what 1 into dh. So that is the tearing load. What about the solid plate strength when there was no rivet hole in that? So that is nothing but pitch into what? What we have formula? Pitch into thickness into sigma t. So tearing efficiency is nothing but tearing strength pt divided by what? P of solid. So that is nothing but p minus dh divided by p. So we can add 1 minus dh divided by p. dh divided by p they have given us 0.25. So 1 minus 0.25, that is 0.75. When you multiply with the 100, you will be getting what? 75 percentage. B will be correct. So in the next class, I will be telling you what is the shearing load or shearing strength of a rivet. What is the crushing strength of a rivet? These are the strength of rivet. But whenever we talk about the plate, then we don't talk about shearing and crushing. Plate will always fail by the call tearing of the plates. Again, plate can also be failed if any of the rivets will fail, right? So we have to consider whatever the load minimum load or minimum strength in which case it has. Either it is not able to survive shearing, or it is not able to survive crushing, or it is not able to survive tearing, right? If it is not able to survive all of three, it will fail. If it is not able to survive shearing but will able to survive crushing and tearing, it will fail by shearing. Shearing means what? There will be shearing of what we call rivet itself. It will shear off. Like when we apply lab joint, it will fail here. It will tear off like this. If rivet itself fail, then how the plate will able to survive? The plate will automatically fail, even though they have good tearing strength. I will be telling you all those things, in our next class. So note down the last problem. This problem is belonging to what? Ball bearings. That is nothing but types of rolling contact bearings. Rolling contact bearings. Again, they are asking the question belonging to load life equations. Load life equation. As I told you, I will discuss separately approximately 10 minutes on types of bearing. I will be telling you all the formula. In that, one formula is there, load life equation, that is nothing but C divided by P equivalent load to the power n, where C is nothing but basic dynamic load rating. Basic dynamic load rating. This will be the constant for all the types of bearing almost. Then we have P is nothing but equivalent load. Equivalent load means combination of radial and thrust load. L is nothing but life of the bearings, either in hours or maybe they will be calculation in RPM, whatever you can have it. N is nothing but N value you just note down. N is there for 3 for ball bearings. N is equal to what? 10 by 3 for roller bearings. I told you we have two types of bearing. One is a ball bearing, other is a roller bearings. Right. So L1 into PE1 cube, that is equal to L2 into PE2 cube. So they have given at one particular load, it has a life of 8,000 hours. When I increase my load to double of that, then how many, till what life it will able to survive? L2 will be what? L2 will be 8,000 divided by 8, that will be 1,000. When we increase the lot of pressure will be acting on a bearing, and it will not be able to survive that much for a longer period, and it will not be able to rotate because bearing will be rotating elements, right? Or maybe if you consider bearing to be a stationary element here, but the casing of that, here there will be balls, right? How many lives it will be able to survive before it first crack will be getting appeared in the bearings, ball bearing. That is called life of a bearings. I will tell the definition also separately. Each and everything we will discuss regarding the bearings, right? No doubt. So C option is correct here. So that's all for today's session. We have covered strength of material machine design of ISRO 2015. In our next class, we will discuss 2016 paper of SOM and machine design. But along with that, we will take some other things about bearings and some of the things about riveted joints and bolted joints, so that in a short period of time, we can cover almost all the things which are required for ISRO examinations. Right? Thank you all.